We are very proud to announce our next speaker, Leandro von Werra. From my own experience, having had him as a collaborator a few years back, I know wherever this guy works, he leaves a lasting mark. It's great. Leandro, he is a research lead at the much appreciated company Hugging Face and a co-author of the very well-known book Natural Language Processing with Transformers. He also co-leads Big Code. It's an open science project for programming code generation with models such as StarCoder 2. He is the creator of a popular Python library called TRL, which combines transformers with reinforcement learning. And now, welcome Leandro. He will tell us about open LLMs, the comeback of open models and current trends in the LLM landscape. The stage is yours, Leandro. Welcome.
Thanks so much for having me and a very kind introduction. So my name is Leandro. I'm a research lead at Hugging Face. My informal name is also the Chief Loss Officer at Hugging Face. I'm responsible to make sure that all the losses of all our models go down. Today I want to talk about a few things. I want to start a little bit by looking at where did we come from and how did we get where we are now in the LLM landscape. I want to talk a little bit about open models and how Hugging Face what part Hugging Face plays in that landscape, and then finally do a little bit of an outlook of trends we're seeing, of interesting things that are coming up. People already started doing some of these things, and where things are going. So it's a lot to talk about, so let's get started. So how did we get here? I think by now there is a very well-established pattern how you get a good language model. You essentially need three things. You need a model that's capable of learning. It has been shown that a large transform model is a really good candidate for such a thing. These days there's not so much innovation on the architecture. Most of the performance gains are driven by scaling and by the data sets. So the second ingredient, the data set, is arguably one of the most important ones. At the scale that we currently are, where we need to train those models, you don't get around to train on the data that you find on the web. It's the only text data that's large enough to train powerful transform models. And finally, you need to train those models, so you need GPUs, you need compute. And the more GPUs you have, the larger the models are that you can train, and hopefully the better you get. But one of the most interesting findings of the past few years, and kind of the reason why we started that whole scaling race where every new generation of model is bigger than the last one, is not just because people were saying maybe bigger is better, but people actually found laws that govern how much better models are as we scale. And these three plots embody this. So they show the loss on the y-axis. So the loss is kind of the error rate of a language model. And on the x-axis, you have compute, you have data, and you have model size. If you do a little trick and you plot this on a log scale, you can see we actually find very nice lines. And why is this remarkable? It's kind of like a guaranteed improvement if you just scale up. And it's kind of it's a very nice trend. And that has led to the scaling race in the past few years. And we can see that by even just looking at what OpenAI has been doing with the GPT models. You see, the first GPT model was trained on 1 to 2 billion tokens, and it had 100 million parameters. For reference, 1 to 2 billion tokens, that's maybe half the size of Wikipedia. So moderate scale. But then they found if we scale this up, if we train these models a little bit longer and make them a little bit bigger, we get better models. And that was GPT-2 essentially, which was trained on 10 times more data and was a model that's 10 times the size, which also means you need to spend 100 times more compute because you need to train a 10 times bigger model and you need to train it 10 times longer. So you get to 100. And that's when people that's around the time when people actually found these scaling laws. It was OpenAI who found them. And they used them to just go further. And GPT-3 is the result of this, was the first post-scaling laws model. And they scaled it up 2,000 times in terms of compute. And they didn't stop there. They went further, and recently GPT-4 was trained on 10 trillion tokens. So that's 400 times Wikipedia or something like that. And it has 1.8 trillion parameters. The absolute cost to train such a model is probably on the order of like $100 million. You might ask yourself, like, who can pay for such trainings? But that's maybe a little bit limited view if you're just in the ML sphere. If you look at like society at broad, there are many places where industry can invest 100 millions to build new things. So if you look at the space industries, a satellite costs $100 million. So I don't think we're quite yet at the point where we stop scaling. A few months after the initial scaling laws, DeepMind released a paper called the Chinchilla Laws. It's kind of a refinement of the scaling laws. And they give like also a very exact recipe of like what's the best model to train given some amount of compute. So in the middle column is the amount of compute you have. It's kind of a function of how many GPUs are in your data center. And then you can see the parameters are the size of the model, and you have the data set size in terms of tokens. And you can find, like, at every compute scale, these Chinchilla laws give you a number for what the size of the model should be and how many tokens you should train it on. So you can, for example, see a 10 billion parameter model should be trained on roughly 200 billion tokens. Now, it seems like nobody told the Llama team that those Chinchilla laws, because if you look at the Llama models, the Llama 3 model is an 8 billion parameter model, and it was trained on 15 trillion tokens. That seems like pretty far off what the Chinchilla laws would suggest. So either the Chinchilla laws are wrong, or maybe there's something else going on. And the way to think about it is the Chinchilla laws just tell you what's the optimal amount of training compute to get the best model. But for many use cases, you're not only interested in training compute, you're also interested in inference compute. You need to deploy those models at some point, right? So maybe it's worth training a smaller model, even a little bit longer, even if it's not fully efficient and Chinchilla optimal, but you get a much more lightweight model that you can deploy in production. And you can actually replot the Chinchilla scaling laws in this plot. I promise it's the most complicated one I'm showing today, but I think it's worth looking at it. So let's first look at the orange line. The orange line is kind of like the compute overhead you're paying over Chinchilla optimal. So Chinchilla optimal, this is plotted for all the 7B models. And you can see where Llama 1, 2, and 3 roughly lie on that scale where they were trained. And the Chinchilla optimal scale for a model of the size of 7 billion parameters will probably be around 250 billion tokens. So it's almost at the origin of that plot. And as you train longer, you pay a compute overhead. So you can see at roughly 10 trillion tokens, the compute overhead is 500%. This means you could get a model that's equally good as that 7B model that you trained on 10 trillion tokens, but 5 times cheaper. So you pay a pretty heavy price to train a model that long, whereas you could train a larger model on less token and get a better model, or a same model. So why do you do this? That's where you have to look at the blue line. The blue line shows you how much you save in inference cost. And you see roughly where those 250 billion tokens are is where the blue line is at 100%. So that's your reference point. That's Chinchilla optimal. But as you train longer, the model gets cheaper and cheaper at inference time. And in the end, it converges around 20%. So even though you paid a heavy price to train the model, it's going to be very cheap to deploy in production. It's 5 times cheaper than if you followed the Chinchilla laws to the letter. So that's why we see that current trend where GPT-4 started scaling up, and now these other companies, they're starting to train models, smaller models for longer, and get also similar results. And the community is much happier. Everybody can deploy cheaper models. So the question is, like, who can actually train these models? It's still pretty expensive to do this. Still need to spend tens of millions of dollars to get good models. This plot just saves you inference costs, doesn't save you training costs. And there has been a kind of a nice development in the past, let's say, 16 months, where last Christmas 1 year ago, it looked a little bit like nobody's releasing any open models anymore. There was GPT-4, and there's Anthropic's models and Google's models, but none of them were open. So the question is, like, who's going to pay for these quite expensive models and open source them? And if you look at recent news articles, you can see Meta is investing to buy a cluster that has 500,000 GPUs. 25,000 is roughly what you need for 3 months to train GPT-4. So they can for sure train a few models, and they seem at the moment at least to be quite committed at training open models. There are startups like Mistral that are releasing open models, and also Google started releasing more open models like the Gemma models that are a lot smaller than the Gemini models, but they're open. So you can download them and deploy them locally as you want. So one thing that I want to clarify a little bit is, like, the term open source and open models is a little bit conflated these days. People talk about these things, but they mean different things. So I want to clarify a little bit, like, the gradient of open models. So on the one extreme, you have the closed models, and I think those are maybe the ones most people are familiar with. You have ChatGPT, GPT-4, Gemini, or Claude from Anthropic. They're what I would call, like, closed models or API models. You don't have access to them. You can just interact with them through an API, so you can't run them locally. You don't have any access to the model's internal state, so you can't really investigate what's going on. And you're limited in terms of fine-tuning capabilities by whatever these platforms offer. Some of them might give you, like, a fine-tuning endpoints. Some of them might not. So that's a little bit limiting, although these models are very good. Then in the middle, you have open model weights. So these are models where the companies, they release the weights of the models, but not much else. And Llama is a case of that. Mistral's model are another case, or there are also a lot of Asian models these days that are really good, like DeepSeek or Gwen. But they don't release anything about their training code or their training data, which limits a lot what you know about what went into the model. So if you're a content creator, you're somebody who maybe builds GitHub repositories publicly, you don't know if any of those models used your code during training. And you have no way to remove any data that went into them. There's other things. You can't really investigate the biases of these models as good as you could if you had access to the training data, because usually they're kind of transmitted from there. And there are a few other, like, more scientific issues where you can't really reproduce the models, and you don't really know if the benchmarks were really decontaminated or if those models are just that good because they trained on benchmarks. And then you have the last column, which is a little bit a rare breed at the moment, which are the fully open models. So those are models where you have access to the training code, you have access to the training data, and the models are released with a permissive license. Reasons why people don't always release the models like that is, on the one hand, maybe the data, or most likely the data is your competitive edge over everybody else. So you created a really good data set, you don't want to release it. You have liability issues. So if you release your data, it's much easier for someone to check if you use their data, and they can sue you. And if you're just, like, vague about it, makes it a little bit harder. And if you open source anything, you have to maintain it, so that's always a little bit an additional burden. So as I said before, it's like, I think these open models are really cool, and they bring a lot of value, but who can train them? Are we just, like, at the mercy of Meta or a few tech startups to do this? And one thing that I found a bit surprising when I started looking into this, like, a year ago, is that actually in Europe, there's a number of, like, open clusters, compute clusters. So for example, there's Lumi in Finland, which is a scientific cluster with 10,000 GPUs. There's Jules and Jupyter in Germany, Leonardo in Italy. Sadly, it's not Leandro, but I can maybe still get access to it someday. And in Switzerland, we have Alps. Alps is probably one of the most potent supercomputers among those. And it's coming online right now, and it's in Lugano. So even in the academic setting, there's still hope that like we can catch up to these closed models, and there is like actually open compute to do so. And then on the notion of catching up, a lot of people, when ChatGPT was released, were a little bit like defeatist. It was a bit like game over. OpenAI is so far ahead, they spend so much money, we have no chance ever catching up. But if you now actually look at the development of the past 18 months, you can see the green line is the performance of open models, and the purple line is the performance of closed models. So clearly, open models are catching up to all those closed models, which is great. The community actually has the ability to do great things if they have access to those models. So that's nice. So where do we see like the closed versus open discourse going? And I think what I like to think about is like a metaphor from software development, where there was a similar question like 20, 30 years ago, which was like, should a company develop their own software stack, or should they just buy whatever Microsoft's building? And I think the answer is there's going to be a compromise. So for a lot of things, it's okay, or even the cheapest, to just use like a closed model. It works out of the box pretty well. But for a lot of use cases, if you have like a high quality data set that's like very domain specific to your business, and you fine tune an open model on that, even now when the models haven't caught up like fully to the closed models, you can surpass GPT-4 performance if you fine tune it right. So I think there's going to be a place for both, where for some use cases, maybe the closed model is the best, but for some other use cases, fine-tuning with high-quality data is still going to be a thing, which I think is common knowledge if you've worked in data science for the last 10 years. So I don't think there's anything fundamentally new here. So I want to talk about like two projects that we've been involved in the open space a little bit. One is Big Science, which is a little bit older, and the more recent one is Big Code that I've been more involved in. And Big Science was kind of like the starting point for Hugging Face, and it was right at the time when GPT-3 was released, and there was no clear sign that anybody else would open source something like GPT-3 anytime soon. So one of the founders of Hugging Face, Tom, who's leading the research team, was thinking like, how could we build an open GPT-3? How would something like that look like? Should we just do it at Hugging Face, or should we do it in a different setup? And he's a physicist. I'm also a physicist. A lot of people in ML are physicists. So clearly our inspiration goes to projects like the LHC, the Large Hadron Collider, where it's like, it's a very expensive machine, but there's a lot of people working together, building something cool of it. And we thought, let's maybe try to build GPT-3 in the open in a similar way. So as an open science project where a lot of people can contribute, and we somewhere find the compute to do it together. And that's roughly how Big Science worked. So in the end, I think there were over 1,000 researchers and collaborators from all over the world participating. We built a multilingual data set called Roots, which is a 300 billion token data set in 59 languages that we built from scratch. And we had to build filters for each language to make sure like the quality is high enough. And then in the end, we trained it on Chancé, which is a public cluster in France, where we could use 400 GPUs for a few months to train Bloom, a 175 billion parameter model. After Big Science was roughly when Microsoft and OpenAI released Copilot. So naturally, we're thinking maybe something similar is needed for code. And so I started co-leading the Big Code project, which aimed at exactly the same thing. Can we build like a really strong code model in a collaborative way rather than as a closed lab? And it's a collaboration between Hugging Face and ServiceNow. It's kind of the two institutions paying for the compute, but we do it fully open. So we have full data transparency. We're open sourcing every tool that we need to build those models, and we release the models in the end so everybody can deploy and use them. The first thing, as I said, and the most important thing is you need a very high quality data set. And there wasn't any code data set at the sufficient scale at that point, so we had to build our own, which we called the stack. To build the stack, what we did is we went to a platform called GitHub Archive, which kind of archives everything that's happening on GitHub. And we retrieved 200 million GitHub repository names. And then what we did for roughly 3 months is git clone. So we had a cluster which was literally just git cloning everything that we found, all these 200 million repositories. In the end, we only had like 140 million repositories because some of them were private since or deleted. But we had like a 100 terabyte code data set after kind of crawling. We then filtered that for specific licenses. For example, we didn't want to train on binary data or CSV files or text files. We just wanted code files, which left us with roughly 70 terabytes of code. And then we did some license filtering, so we only included permissively licensed code, which is like removed a lot of the data that was originally in the data set, and we had like 6 terabytes in the end. We did a lot of ablations around what makes a good code data set for language model training. You could think of many metrics how to rate good code files. We thought about like maybe we should look at how much comments are in code. It's like, is it well documented, kind of. So we looked at code to comment ratio, or we looked at GitHub stars. We looked at if the tokenizer was efficient, things like that. In the end, we found like nothing really helped significantly. The one thing that made things much worse was looking at GitHub stars. So GitHub stars are not really an indication of high quality code, sadly. The one thing that we found always improved the quality of the models was deduplication. So we ran a very aggressive near deduplication where we not only remove data that's exactly the same, but also very similar. So that removes a lot of the code file, the config files, for example, where only like one field, for example, changes. And with that data set, we trained a family of models. It started with more like a small model that was a side product of the ablations that we ran that we called Santa Coder because we released it at Christmas. And then we went on last year in May, we released Star Coder 1, which was the state-of-the-art code model at the time for about 3 months. That's roughly like the timescale in the LLM world at the moment, whereas like we were state-of-the-art for a few months, so that was good. And in February, we released Star Coder 2. And you can see when you look at like the cost, the languages, and the tokens, how we also scaled up, essentially. It's like the models got bigger. We didn't increase from Star Coder 1 to Star Coder 2 too much the size, but we increased the number of tokens that we trained on and the number of languages. So Star Coder 2 knows 600 programming languages, more or less, which is more than I thought would exist. And for me personally, one of the most exciting things about building things in the open is that you start to build kind of an ecosystem. So since we released the stack, every code model that has been trained since has been trained on the stack. So people are reusing the tools that we built. And even some of the closed models that don't publicly disclose what they were trained on, we know that they actually also use that data set. So it's like something that has a lasting effect. And similar for the model, many people have taken the model and fine-tuned it on specific things and reached like great performance. And the SQL coder is, for example, one example where people fine-tune on text to SQL, and they were able to beat like ChatGPT, whereas the model is much smaller than the OpenAI models. So that's one example of like good fine-tuning gives you an edge. So before I close, I want to talk about 2 things briefly where I think things are going a little bit. And one thing that we clearly see a lot of more interest recently is agents and tool usage of these models. So traditionally, when you use a language model to answer a question, you pass the question, and then you expect the model to produce an answer straight away. But this can be quite challenging, for example, in this case, where the question is like, how many inhabitants do the capitals of Switzerland and France have combined? It's kind of a multi-step reasoning, and you need to have some knowledge about things. That's pretty hard for models. But if you let them do do intermediate step where they can use tools, they can solve these tasks quite easily. So they could Google what's the capital of Switzerland, how many inhabitants are there, and then maybe in the end even use a calculator to sum the numbers. And I think we're just at the start of this, where at the moment, like, people do like 1, 2-step things, but you could imagine in the near future where it's like you want to know something and the model goes around the internet, maybe queries thousands of web pages, maybe watches some YouTube videos about the topic, and then comes back with a much more in-depth answer a little bit later. The second thing, I think, especially since GPT 4.0 came out, is like we're moving away from just like text to text to multimodality, where these models are capable of understanding more and more modalities. On the one hand, this is also a question of like, where do you find the next tokens? We're now training at like 15 to 20 trillion tokens. That's kind of almost all the data you can find on the web after you filtered it. It's like, so how could you double it or 10x it? And the answer is like, if you maybe go for other modalities. So if you look at images as well, or you look at videos, audio, there's a lot of data that we're still not using to train those models. And in addition to just having more knowledge, you also have more combined knowledge where these models understand better, like the interplay between a video and audio, for example. Whereas the text models, the only thing they've ever seen is text. So it's hard for them to understand like a description of something visual, for example. With that, I would like to close my talk. I think I'm roughly on time. And so I have some time to answer some questions.
Thank you very much, Leandro. I guess he's our star coder, Leonardo, I guess. So I'm sure there are questions. Many. Come on, don't be shy. You can even touch him. Over there.
Thank you very much.
Hello. It was a great talk. Actually, should I go? Yeah. So it was a great talk. Really enjoyed it. So my question is more related to mixture of experts. So currently the new models which are coming in, like DBRX and Mixtral, so they are using mixture of experts rather than having a whole single model, right? So what are your thoughts about it? Means, is it the future or is it something that will go on?
Yeah, I think mixture of experts are probably something that are going to stay. I don't think they changed the game too much in terms of like performance of models. They're not going to make the language models inherently better. The main reason you want to have a mixture of experts is during inference time. You don't actually need to activate the whole model all the time. So a mixture of experts kind of routes information to some experts of your model. So at inference time, it's great. You have a model that's huge, but you only actually need a subpart of that. So the way it looks like, people are still quite excited about a mixture of experts, and I don't think it's going to change anytime soon.
Thank you very much. I have a quick question. You mentioned the number of tokens and the effect on the quality of the model. How about the quality of the tokens or the input itself?
Yeah, I think that's like a tough interplay, especially you as someone who wants to train a model. You know, the more tokens you get, the longer you can train, and the higher the likelihood that your model is great. But at the same time, if you train on garbage, then your model is going to be bad. So it's a trade-off where you don't want to filter too much, so you don't have enough tokens anymore. And also, in general, it's a pretty good idea to have a little bit of noise in your data. These models are so robust because they have seen a lot of different things, so you don't want to throw away like whole subfields. There is a really good data set called C4 by Google, and part of their pre-processing pipeline was removing documents that have that are in a blacklist of words, and one of these words is sex. So the model has no idea about the whole concept around sex, not only filtering out porn, but like the whole biological half of that word, the meaning of that word, right? So that's probably too far, but removing like a lot of porn, or if you actually look at like what the web looks like 95% of web data is garbage. It's like It's porn, it's obituaries, a lot of them, surprisingly, a lot of people dying and putting it on the internet. And you need to filter a lot. So if you train for, you usually start with like 100 trillion tokens, and we filter down to 10 trillion tokens, 15 trillion tokens. And at the moment, we're in the phase where we still filter down a little bit more, and we still find we can squeeze a little bit out of the models. But it's a little bit of balance where too much filtering makes the model worse, not enough filtering makes it also bad. So you need to find somewhere in the middle where it's like you actually gain performance. It's not a universal answer, sadly.
Thank you, fantastic talk. With increased usage of large language model, the web is also getting polluted with AI-generated content. What's your view on the future of training?
Yeah, so we're currently running an interesting analysis where we processed like the whole web, and we have like kind of a time series of the quality of different snapshots of the web. And what we also started looking at is how often does the word, for example, delve, appear in each of the dumps, and we can see like the quality of the dumps goes up, and also the number of times delve appeared in those dumps. So we're definitely seeing that we have more contamination, but as I said, like the average quality of the web is really low. So actually, ChatGPT data is way above the average quality, but at some point, maybe you're right, it's going to be 95% ChatGPT, but I think as long as we have like mechanisms like deduplication, where we can remove content that's too similar, or we have other mechanisms, for example, you can look at PageRank, you can see like which websites people actually like to look at, and you can take data from those web pages and upsample them. So I don't think we're currently like in immediate danger that the models are going to be very bad because we trained on too much model output. And you always have the second half of the model interaction too, right? Which is the questions that people ask, and the follow-up question, which also gives interesting signal.
So my question considers your statement that there wasn't much of innovation regarding the transformer architecture or architectures in general.
Mm-hmm.
However, lately I've heard that XLSTM and Mamba and Jamba are popping up, and people are saying like this is the future, transformers are going away soon. What's your opinion on that? Maybe you already gave it away in your talk, that you, but still, can you elaborate a little bit?
No, I mean, I think those are definitely interesting developments, and I'd be happy if there would be a new architecture that's like beating transformers. It's a little bit boring from the modeling side at the moment. At the same time, like Jamba and Mamba and so on, they don't really change the game in terms of like how good is your model during training. It's like if you look at the scaling laws kind of for different model architectures, they all look the same. So it's like you train on the same amount of time, you kind of get the same performance. What's interesting again about these Mamba models, for example, is like they're faster at inference time. So people are thinking more about like how could we change things that like they're easier to serve, and I think that itself is like a valuable development. That being said, there is also a different aspect to it, which is the whole industry is building a stack at the moment towards transformers. So there's like almost down to the hardware level, people are optimizing the stack to be really efficient for transformers. And for every new architecture, you kind of need to catch up to all the optimization people have done on transformers. I don't know if you know, for example, Flash Attention, which is like super efficient library to train the transform models. It computes the attention very efficiently. Everybody uses that now. But somebody needs to do that for all the new architectures too, right? It's like, it's kind of a GPU optimization. And that's why it's like, you need to see like significant benefits to have like the whole industry like start optimizing for a new stack. Yeah, for sure.
Hi. So you show in the chart that open source models are catching up, so which means that either they are faster to catch up or the closed ones are slowing down. GPT from 4, we didn't get 5, we get 4.0. And from the presentation, the value proposition was, it's faster, it's cheaper. It didn't felt like, you know, like a leap forward. Do you think we are reaching like a flattening part of the curve?
I don't think so. So there are several levels at which you can optimize things or you can get better performance. And currently, there are like 3 major ones, I would say. So one is scaling. That's like the easy ones. Like if you take the same data set, if it's big enough and you train a better model, you're going to get better performance. And if you look at like how many GPUs Meta buys or like how big the data centers of Google are, I don't think we reach quite the maximum of how big model you can train. So once maybe you exhausted that a bit, you can always go to the second level, which is data. So if you create higher quality data sets, then you're going to get better models as well. So a lot of the progress we're actually seeing in the open model space is not, they haven't been scaling as fast as OpenAI. Those models, the biggest one, are all roughly 70 to 100 billion parameters, but they have been scaling the data a lot and improved the quality. So even though maybe you reach a little bit the limits of how big a data center you can build without like having a blackout in your neighbor village, which happened in Cambridge recently when they turned on their cluster, you can still like improve on the data set side. And then finally, once you exhausted that, that's where academia can shine, right? Which is on architecture innovation, which at the moment it's very hard, as I said, like they all look kind of similar performance, but if you have a lot of pressure to innovate there, maybe there is a better architecture in the end, and then you can restart again from. So I don't think we're hitting a wall quite yet.
The topic of quality, and maybe quantity as well. Do you see synthetic data as a technology that could be contributing to that, or is not really the case?
Yeah, we're also exploring that a little bit, seeing there is this family of models called Phi from Microsoft that heavily relied on synthetic data. They kind of used ChatGPT or GPT-4 to generate data, and then they trained small models on that, and they found they train very quickly to good performance. So I think synthetic data can potentially play a role in it, but I don't think we're going to replace like the whole pre-training data just with synthetic data anytime soon. The other like idea people like about synthetic data is that you can maybe get around copyright issues where you generate new content rather than using copyrighted content, but I think the jury is still out if that's actually a solution or if it's just like copyright washing, where it's like you train a model on copyrighted data and then you generate new data and you say that's not copyrighted anymore.
In terms of more software aspects, like we've talked about, or you've talked about copyright, or like just how open models allow for, let's say, more auditing. But where do you see the biggest like societal challenges for, or software challenges for open models?
You mean in terms of like as the software that's on the web that's being used to train those models, or the software stack to train the models?
Excuse me, not software. Like I mean, we've talked about a lot about performance, how open LLMs are catching up to closed source LLMs in terms of like accuracy or other performance metrics. But where do you see the next big challenges in terms of non-performance goals? Like
so like how easy it is to use those models, for example,
for instance,
or train those models. Yeah, so I think that's where we see a lot of improvement since there are open models. Like Llama 1 came out last January or something, at the beginning of last year. And since then, people have been innovating a lot on like how can you actually fine-tune those models. Whereas like if you asked me 2-3 years ago, can you run a 1 billion parameter model on your laptop? I would have said like no. It's like you're gonna melt it. And now people are running like Mistral 7B on their Raspberry Pi, and it seems like working reasonably well. So I think there's a lot of innovation coming, and it has become also a lot easier to train those models. There's, for example, this technique called parameter efficient fine-tuning, which allows you to fine-tune these models much cheaper than it was 2 years ago, and that's kind of a result of both having people thinking about these problems and having access to models. So I think today it's the hardest to train the models. It's like it's only going to get easier from here on. Yeah.
One last question, just to stretch it.
Keeping everybody from upper row.
Looking at the future of models, will we have a large zoo of very specialized model, one for SQL statements, or will we go towards more generic, ready Swiss Army knives kind of models?
Yeah, that's what I was trying to hint a little bit at in the open versus closed discussion, but it's like applying more generally, where I think there are use cases where you kind of already saturate with some models that are out there today. For example, if you ask write me a poem about X in the style of Y, I think most models are doing it quite well, and it's hard as a human even to see an improvement. And I think a lot of use cases people have that are a little bit like ChatGPT, where you just want to ask it random questions during the day of rephrasing an email or something like that. I don't think you need specialized models to answer an email. I think ChatGPT can do that already reasonably well. But as you go to more specialized cases where, for example, you want to have a coding assistant or a model that reviews your code or writes tests for your code, that's more likely where you want to have specialized models that perform really well. The other way I like to think about it is also, if everybody's using ChatGPT, then nobody has an advantage over everybody else. So it's I think if you build your own very specialized high quality models, that's where you have an advantage. And it's similar, nobody reinvents Microsoft Outlook these days. It's it works well enough for most use cases most companies have, but every major company now has a software department building their own specialized software stack.
Wonderful. Thank you very much, Leandro. This was really insightful.
Thanks a lot for having me.
Merci. And a little present.
Yes.